Good morning, everyone. Today we will continue our topic. Today we will go through a few examples and questions. So let's start with this question. The question reads the following: which of the arrows best represents the direction of the net force on a charge plus Q due to the other two charges? So what are those other two charges? We have positive 4Q and we have a positive 2Q. We need to decide on which one represents the correct answer for the net force. So here we have the distance is the same. So this is the plus Q, right? And then we have the plus 2Q, and we have here the plus 4Q. So if I adopt the colors, let's make the distances the same. So the distances here are the same. This is D. We need to calculate the net force exerted on the plus Q due to the plus 2Q and plus 4Q. Okay, so if I take the color red that represents this positive 4Q, then I will draw the force. The force is going to be on the same line between both charges and pointing this way such that it is a repulsive force. So let me call this one F1. Now if I take this one to be blue, so I can represent the force exerted by this plus 2Q on the plus Q. And again, it is a repulsive force because they are both are positive charges. So F due to the Q2 positive 2Q on this plus a Q, positive Q, will be F2. Now notice that this charge is 4Q twice the charge of the plus 2Q. So if I am to write the magnitude of the force, F equals 2, okay, Q1 magnitude, Q2 magnitude divided by R squared. In this case, if I write F1 as K, Q1 as 4Q, Q2 as Q divided by D squared, then F2 as K times 2Q times Q divided by D squared. We can notice that F1 as a result, I have F1 equals 2F2. So the magnitude of F1 is twice as the magnitude of F2. In this case, if I want now to calculate the angle, so this is F2, and now my total force, my net force, is going to be this one. Now here I only care about the direction, which means I am interested to know this angle, theta. Then theta is tan inverse of F2 over F1. So theta is tan inverse F2, which is half F1 over F1. Theta is tan inverse 0.5, and then theta would be 26 degrees. So the answer is B. Okay, we have the solution here. Let's move to the next question. And this question, we have the following: two balls with the charges plus Q and plus 4Q. So this charge is 4 times the charge of the red ball. They're placed or at a fixed distance, 3r apart. The question is it possible to place a third charge, Q naught, on the line between two charges such that the net force on the Q naught will be 0? So my question is asking if it's possible that I put a charge right in between those two charges such that the net force would be 0. Is that possible? Let's evaluate it. So I have here plus Q. I have here plus 4Q. And this is the line. The distance is 3r. Okay. So if I bring a charge Q naught here in between, let's assume that this charge is positive. I'm just trying to understand if it's possible or not. Then what are the charges? What are the net force would be exerted on this Q naught? If this is positive and this is positive, then definitely, if I pick this red, then definitely the force exerted on a Q naught due to this charge would be a repulsive force and pointing in this direction. Let me call this one F1. Now, if I take this one to be red, blue, then the force also exerted on the Q naught due to this charge, both of them are positive, is also a repulsive force and pointing in this direction. Let me call this one F2. Now, is it possible at a point between those two charges where F2 becomes equal to F1? Yes, it is. It is possible. This charge is 4 times this charge. Then definitely I will get to a point where there is a point in between where F2 equals to F1, right? They're in the opposite direction. So if I slide this charge, this positive Q naught, to the left, I will find a point where F2 equals to F1. Now, what's going to happen, and we can prove this mathematically. If you take F1 to be K for Q times Q divided by distance could be X squared, then F2 will be K times 4Q Q times Q naught divided by 3R minus X squared. So yes, I can find, if I equate those two, I can K for Q times Q naught divided by X squared equals to K times Q naught divided by 3R minus X squared. So K, Q naught is going to cancel. You'll end up with 4 over X squared equals to 1 over 3R minus X squared. Here I assume that the distance here as X, then the distance here as 3R minus X. So I should be able to solve this equation and find a value for X where F1 equals to F2. We can do that. So for the positive Q naught, yes, I can find a point where the force is going to cancel. Now let's evaluate the negative. So if I have here 4Q and here plus Q, again, if I bring Q naught, and this time it's negative, so what's going to happen? Again, if this one is red, then the force exerted on the Q naught due to this 4Q will be an attractive force. So this one will be pointing in this direction. Now the same thing is going to happen for this charge. Because this one is positive and this one is negative, the force is going to be attractive as well. So both forces are opposing each other, which means I will find a point where F1 would be equals to F2, and then magnitude, and since they are in the opposite direction, then those two forces would cancel each other, and the net force would be zero. So, what is the conclusion? Of course, it can be solved, the same way we did solve here. Again, solving this one would be an x squared. We want to massage this a bit. It will be x squared equals to 4 3r minus x squared. There will be a solution, a quadratic equation. There will be a solution where for x such that f1 equals to f2. Same thing applies here. There will be a point where f1 will cancel f2. So what is the conclusion? The conclusion is if q naught is positive, there is a possibility that the net force would be zero in between plus q and plus 4q. If q naught is negative, there is also a possibility such that the net force exerted on this negative q naught would be also zero. Here the forces are attractive forces, but they will be in the opposite direction. However, here the forces are repulsive forces, however, and they are also in the opposite direction. So back to the question, the right answer is yes, regardless of the sign of Q naught. Okay, so those are exactly what we were talking about. Now let's move to this question. In this question, we have the following. We need to calculate the net force exerted on the proton P due to an electron and due to an alpha particle that is a helium nucleus, which has two protons and two neutrons. So regardless here of the sizes, as we see here, alpha is bigger than the proton, we will ignore those sizes and we'll treat them as point charges. Okay, so let's solve this problem. We need to calculate. So what's the difference between this problem and the problems we have seen earlier? The only difference is those charges, they are not on the same line. In this case, we will deal with projections. We'll have to do some projecting the forces and find the components of the net force and then reconstruct the net force again. So let's get started. So 1.2, 55. So I have here proton. That's the alpha, and this one is the electron. So I will call this one Q1, which is this is the alpha, which is plus 2e. This one I will call it Q2, which is the proton 1e. So this one is plus, and this one Q3 minus e. The angle here is 55 degrees. and the distance here is 1.4 10 to the power minus 10 meter, and 1.2 1.2 10 to the power minus 10 meter as well. So we need to calculate the net force exerted on the Q2. My coordinates are the following: X, Y. So I have here positive 2e. If I assume this one to be red, and I can see that both of them are positive, then this force is repulsive force. I will write it as F1. And the second one, I'm using the colors just to make things easier for you, such that you know which force that is exerted due to which charge. Here, this is negative. Positive force is attractive force. Then it will be pointing in this direction. And let me call this one F3. Okay, so this is F1 due to this one. This is F3 due to Q3. I need the net force. Then I need to calculate first the values of those forces. So the magnitude of F1 is K times Q1 magnitude, Q2 magnitude divided by R squared. What is the R squared? 1.4 10 to the power minus 10. So I have here, let me put it here, F1 equals to 8.99 10 to the power 9 times Q1, which is 2, 1.602 10 to the power minus 19, Q1, Q2, also magnitude, 1.602 10 to the power minus 19, divided by 1.4 10 to the power minus 10 squared. In this case, F1 equals 2.35 10 to the power minus 8 Newton. F2 is 8.99 10 to the power 9 times Q1 is, again, magnitude, which is 1.602 10 to the power minus 19 times Q2 is plus 8 magnitude, 1.602 10 to the power minus 19 divided by 1.2 10 to the power minus 10 squared, and then F2 is, I'm sorry, this is F3. We called it F3. F3 is 1.6 10 to the power minus 8 Newton. So this force is due to the Q1 that I called it F1, and it is repulsive, and this force 1.6 to the power minus 8 is due to the electron, and it is attractive, as you can see here. Now what I need to do, I need to calculate the net force. So how do I calculate the net force? Let me redraw again here with focusing on those two. So I have F1 and I have F3 and I have the angle here as 55 degrees, and I need to calculate the F total. So in this case, what I'm going to do is I'm going to project this F3. So as I said, I'll take this as X, Y. Then my F tot would be, I will project F3 on the X. Gonna give me this. So this one is F3 cosine 55. And this one is F3 sine 55 degrees. So now I have X components and Y components. So let's put together the X component and Y component. I have Fx, that is the summation of F1 plus the F3 cosine 55 degrees. And I have Fy, which is only F3 sine 55 degrees. So if I am to plug in those numbers and do the calculations, I can find X to be 3.27 10 to the power minus 8 Newton, and Fy to be 1.31 10 to the power minus 8 Newton. Then the total F would be F tot would be Fx squared plus Fy squared, and in this case F tot would be equal to 3.52 10 to the power minus 8 Newton, and the theta is tan inverse Fy over Fx, and then this is going to give me theta equals to 21.8 degrees. Now let's look at that force. So again, this force is going to be due to the summation of those two components. So let me, if I add those two vectors, I will get this vector something like this. So we'll be adding this vector. This one is fx, and this one is fy. So this one is f tot, and this one is the 21.8 degrees. Okay, so the solution is also here. The notations may be different than the one that we have adopted, but that's all right. You can choose wherever you want as long as you formulate your problem correctly. You should be able to get the same answers. So let's move on to this example. Here in this example, we have two particles A and B with a charge QA 7 × 10⁻⁶ Coulomb and QB with also a positive charge 2 10 to the power times 10 to the power minus 6 Coulomb respectively, and are separated by a distance of 1 meter. Where along the x-axis can a third particle with a charge Q be placed such that it experiences a net electrostatic force equal to 0? This is the same of what we have seen earlier when we were asked about what kind of charge that we can put. Is it possible that we put a charge between two charges from the same type such that the net force in between would be 0? We said yes. And here also we have A and B from the same type. Both of them are positive. So putting a charge in between would definitely have a solution such that the net force would be 0. Let's solve this problem and we'll see how we do it. So we have QA 7 microcoulomb, QB 2 microcoulomb, and a distance of 1 meter. So the problem is I have a QA. There's red for this one and blue for the other one, QB. So I have a QA as 7, QA QB as 2. Then the distance in between is 1 meter. So I know QA is a greater than QB. So I'm expecting it to be closer to QB. So let me take this one as Q. So in this case, if I assume this distance to be x, then definitely this distance would be 1 minus x. Okay? So let's write the forces. Let me call this one. If I assume that this one is positive, it's not going to matter, positive or negative, but if I assume that this one is positive here, in both cases, there will be, the forces will be in the opposite direction. So I'll put this one as FA. And this one as FB. And now I will calculate FA. FA equals to K. QA. Q1 here is QA times Q divided by R squared, which is X squared. FB as K QB. Again, all of them are magnitudes divided by the distance here is 1 minus X squared. Now, I need to calculate for X when FA equals to FB. So here, K, QA, Q divided by X squared equals to K, QB, Q divided by 1 minus X squared. Q is the same, is going to cancel. K also is going to cancel. So I ended up with QA over X squared equals to QB 1 minus X squared. So let's substitute now. QA is 7 power minus 6 over X squared equals to 2 power minus 6 1 minus X squared. 10 to the power 6 is going to cancel. So this is going to end up to be 7 1 minus X squared equals to 2X squared. So 7 1 minus 2X plus X squared equals 2X squared, and this one as 7 minus 14X plus 7X squared equals 2X squared, or 5X squared minus 14X plus 7 equals to 0. Quadratic equation. I need to solve this equation. So I have X equals 2 minus B. So this one, just to refresh your memory, if this one is A, X squared plus B, X plus C equals to 0, the solution would be minus B plus minus b squared minus 4ac divided by 2a. So x is 14 minus b plus minus 14 squared minus 4, 5, 7 divided by 2 times 5. So the answer is x equals to 2.1 meter or 0.65 meter. So this answer falls outside, which is basically a trivial solution. Why? It has to be in between. If you want the forces to be opposing each other, we said it has to be in between. The solution of 2.1 meter basically means that the point is somewhere outside in this direction. And in this direction, the forces will not be opposing each other. Why? Because here in this direction, this is a Q, then FA would be in this direction, and also FB would be in this direction. So the net force will never be 0 if the solution is 2.1 meter. So the solution has to be in between, which means that the solution has to be less than 1 meter. Then that's why the next solution, which is the 0.65 meter, is the correct answer. So at a distance of 0.65, if this is 1 meter, and this is half a meter, so it's exactly the same, in the same direction as I expected. It will be far from the high charge, closer to the lower charge, and this is where we got this point, 0.65 meter is the point where if I put any charge in here, positive or negative, the net force on that charge would be 0. Again, the solution is also written here for you. Last question is asking what is the net force at Q on the x-axis, and this one, what is the net force at Q on the y-axis. So the question is looking for the two component of the net force, the x component and the y component. The solution is given to you here. One comment I need to mention here. I would like that you solve this question and then we can solve it together later on. But what I want you to pay attention here to is why Fy is 0, why the net y component on the charge Q is 0 due to the symmetry. Due to the symmetry, as you can see, just by inspection, this is positive, positive, then the force exerted on this is in this direction. And as you can see, Q2 also are the same. So due to symmetry, those two forces are going to be magnitude-wise equal. So if I project this on the X component is going to add. If I project this on the Y, the Y component are going also to be equal, but in the opposite direction. However, they will cancel. That's why Fy in this problem is 0, and Fx, you can calculate it. It will be the same. Calculate the magnitude using KQ1, Q2 over R squared, and then calculate the angle here, then projected on the x-axis. It will be twice this projection because due to the symmetry, the Fx for the first force will be equal to the Fx of the second force.